Alright, this is going to serve as an introduction into the next chapter, which is chapter 7, which focuses on atomic structure. First thing we're going to start with is talk about the nature of light. A lot of times in chemistry there's a discussion, same thing in physics, of whether light is a particle or a wave. Well, there was basically different sets of evidence that said that light was made of particles because one, it traveled in a vacuum, was able to reflect off objects and exerted force. The other school of thought was that light has to be waves because it reflected like waves, it refracted and diffracted and then exhibited interference. But then basically the idea is that basically light, the duality of light means that sometimes it acts as a wave, sometimes it acts as a particle. So it has properties of both, and we're going to talk about those properties. Waves, when you talk about waves, key thing is wavelength. What does the wavelength represent? It's the distance for one wave to go through a complete cycle. Usually like crest to crest or trough to trough. Amplitude is half the vertical distance, the top to the bottom of a wave. And then frequency is the number of cycles that pass a point in a given second. In chemistry and physics, we measure frequency by seconds or hertz. You'll see that in a little bit. So wavelength and amplitude. Here's an example of wavelength right here from crest to crest. You could do it from trough to trough. That's wavelength, distance of one wave. Amplitude is half the height of the wave. When you talk about frequency, you're talking about in a 1 second, also called the hertz, how many waves pass by in a given second. So if you look at these two in this picture right here, notice I have 1, 2, 3 waves going by. I see 3 waves in 1 second, whereas on the bottom one I see 1, 2, 3, 4, 5, 6, 7, 8, 9. When it asks you which of the ones above has a higher frequency, it's going to be this one right here. You have more waves for a given second of time. So when you talk about frequency, you're talking about the number of waves. When you talk about wavelength, you're talking about the distance. Notice how this wavelength is shorter, this wavelength is longer, which tells you the fundamental relationship between wavelength and frequency is inversely related. Think of a teeter-totter. If you have wavelength on one side, frequency on the other. If wavelength increases, frequency has to decrease. And frequency and energy, the more frequent waves are, the more energy you're going to have. It's going to be delivered. So frequency and energy are directly related. So that's one example. You could also say what happens if you increase frequency. If I increase frequency or energy, wavelength then has to decrease. That's the idea of the inverse relationship. One of the things in chemistry you have to be aware of is you have to understand that there's different regions to the electromagnetic spectrum. So if you think about it this way, radio waves, which we're all familiar with, tend to be very large. Microwaves, a little smaller, powers our cell phones. Infrared powers like our remote controls on our TVs, even smaller. Wavelength, but a little bit greater frequency. Visible light, which we're all familiar with, Roy G. Biv. Ultraviolet light, which is like from the sun, is an example. UV, you put on the sunblock. X-rays, and then finally gamma rays. As you notice, you go this direction, what the wavelength shrinks. So wavelength is decreasing, the amount of energy is increasing. When you compare the sizes, like in a human-centered world, a radio wave is about the size of a building, whereas a gamma ray is about the size of a nucleus of an atom. That's why it has such a great frequency. As wavelength decreases, frequency increases. You need to know all the 7 parts or the 7 major areas of the electromagnetic spectrum. You talk about visible light. You have visible light wedged in right here, Roy G. Biv. A couple key things. The unit for frequency is hertz, which just means per second. The S minus 1 means per second. That's what it's referring to. The relationship is what I call it the speed of light equation. It's frequency times wavelength is equal to the speed of light, which is 2.998 times 10 to the 8th meters per second. I just round that off. So if you look, how do we use this equation? Well, C is a constant. That's never going to change. That's the speed of light. So all you really have to do when you have to either find frequency or wavelength, they'll mention both in the problem. They'll either give you, in a typical chemistry problem, they're either going to give you frequency or they're going to give you wavelength, one of the two. This is a constant, this is always the same. They give you one of these, you have to solve for the other. So on this one, they mention frequency and they mention wavelength. Key things you need to know: wavelength must be in meters and frequency has to be in hertz. So you have to use your conversions. Notice wavelength is in nanometers, which is given a lot in atomic structure. How do we deal with that? Well, the way we deal with that is you take the 8.21 nanometers and you say that 1 nanometer is equal to 1.0 times 10 to the negative 9th meters. That's your conversion factor. So when you multiply this all the way out, you end up with, you get 8.21 times 10 to the negative 9th, and you convert it meters. That's the value you're given for wavelength. So this is wavelength right here. So after you convert it to 8.21, so we're going to convert this to 8.21 times 10 to the negative 9th, what you're going to do is you're going to set it up in the equation. So if I'm given wavelength, which is going to be 8.21 times 10 to the negative 9th, plug that in there, I'm solving for frequency equals 3.00 times 10 to the 8th meters per second. This is in meters here. Notice meters is going to cancel here, meters is going to cancel there. You're going to cross multiply, you're going to put the 8.21 times 10 to the negative 9th here. This is in meters, so therefore the meters will cancel. So what you're going to be left with is per second, or S minus 1. That's what hertz is, because it's on the bottom of the fraction for the units. Then you're going to divide the two, and your correct answer should be, when you're all said and done, 3.65 times 10 to the 16th S minus 1 hertz. And you get that by just plugging in the wavelength, plugging the C, solving for frequency. Here's another problem. Calculate the frequency of visible light having a wavelength of 485 nanometers. First thing I have to do is convert. So I take 485 nanometers, I divide by 1 nanometer is equal to 1.0 times 10 to the negative 9th meters. What's that going to convert to? I should get 4.85 times 10 to the negative 7th meters when I'm done. Nanometers cancels, I put that into a grid, and what I end up with is I basically take the 4.85 times 10 to the negative 7th meters. Meters cancels, whoops, pen back right here. Meters cancels. I don't know if it's seconds. I divide the speed of light 3.0 times 10 to the 8th divided by 4.85 times 10 to the negative 7th. That's what I get. When they ask you what color visible light that is, you can actually go to the chart. There's a chart in chapter 7 which will tell you what color 485 nanometers are. You would look that up on a chart. Here's another example. CO2 absorbs light with a wavelength. They're giving you wavelength of 0.018 millimeters. Remember, it has to be in meters. Therefore, you have to convert it from millimeters to meters. So what you do is you basically are going to end up with, when you convert this to meters, you're going to end up with basically the C goes on top, wavelength goes on the bottom, so it's going to be 0.018 times 10 to the negative 3rd meters. Meters is going to cancel. You're going to get 1.7 times 10 to the 13th hertz. Remember, 1 hertz is equal to a second. That's what they're talking about. Here's another example. They want to know wavelength. They're giving you megahertz. It's not in a standard unit. All these are about just converting units. So what do you know? You know lambda times frequency is equal to the speed of light. Speed of light is 3.0 times 10 to the 8th meters per second equals wavelength, which we don't know, but we do know frequency. This is in megahertz. Meg is the same thing as a million, so I'm going to convert it back to hertz by going 90.7 times 10 to the 6th, because megas means million, which is 10 to the 6th. So I'm going to get 9.90.7 times 10 to the 6th, goes there. To solve for wavelength, I'm just going to cross multiply. So I put the 90.7 times 10 to the 6th there. That's gone. And that's in hertz. Just the same thing as per second. That cancels, that cancels. So then I'm basically left with meters, and what I end up with when I divide the two is 3.31 meters, because the hertz or seconds cancels or hertz cancels. I'm left with meters. All you're doing whenever you're doing a speed of light calculation is you're taking the one that they give you, putting speed of light on the top of the fraction, dividing by the one that they give you. You just have to make sure the units are correct. And that's what you're going to do for homework tonight. I gave you a bunch of problems. Just make sure your conversions are correct. Remember, 1 nanometer is equal to 1.7, or 1.0 times 10 to the negative 9th meters, to convert from nanometers to meters, and you should be good. All right, have a good evening.